The talk is devoted to the log behavior of the A partition function, to the log behavior of quasi-polynomial-like function. Therefore, at the beginning, let me recall some basic definitions related to these issues. The first of them is a definition of an A partition. So we have a finite multiset of positive integers, and now by n partition of a non-negative integer n, we mean any sequence lambda, which consists of lambda 1, lambda 2, lambda j, such that all of its elements belong to the multiset A. And their sum is, of course, equal to n. And in order to meet some confusion related to the situation in which A1 equals A2, we have an additional requirement that two A partitions are considered the same if there is only a difference in the order of the A parts. And now the A partition function of n is just the number of all A partitions of n. Let us take a look on a simple example. So if capital A is just the following multiset, then there are exactly 8 A partitions of 7, which directly correspond to the following sums. It is worth pointing out that if we allow capital A to be infinite set or multiset, for instance, if capital A is just a set of positive integers, then we obtain the classical partition function, which will be denoted further by P of n instead of this quite the unusual notation PA of n. At the moment, let me also mention about the asymptotic behavior of the A partition function. So it is well known that the A partition function is a quasi-polynomial of degree k-1 if a multiset A consists of k elements. So that's the expression of the following form, in which each of this coefficient Tj depends on the residue class of n modulo the least common multiple of A. Since some of our theorem's results will be valid for slightly more general family of functions, let us also introduce the definition of a quasi-polynomial-like function. So we say that a function g is a quasi-polynomial-like function if g asymptotically behave like a quasi-polynomial. So we can write g in the following form, where once again this coefficient depend on the residue class of n modulo some positive integer m. Great. So now let me say a few words about the motivation for my talk and for my research. That is the log concavity problem. We say that the sequence of real numbers is log concave if it fulfills the following inequality for all n greater or equal than 1. In 2015, DeSalvo and Pak reproved the theorem of Nicholas from 1978 that the partition function is log concave for all n greater or equal to 26. In fact, that result has initiated wide research related to investigating similar properties for other variations of the partition function. However, it also initiated some research related to other inequalities. For instance, the Basnerot-Ono inequality, the R-log concavity, so somehow it's a generalization of the log concavity task, and the higher order two inequalities, and the polynomization of all of the above problems. I would like to talk at least a few words about all of this issue today. So let me just start with the log concavity problem and the R-log concavity task. So we fix a sequence of real numbers C and assume that there is a positive integer R. And now we define recursively the family of sequences Carly L I C hat of n in the following way. So the first one is defined in such a way. And we see that it directly corresponds to the log concavity problem. And the curly L hat C I of n is given by the following formula. And now we say that the sequence C is asymptotically R log concave if all of these sequences, all of these values, curly L hat C of n and so on up to curly L RC n hat are positive for all sufficiently large values of n. And there is a result of Hou and Zhang who proved that the partition function is asymptotically R log concave for every positive integer R. So what about the A partition function? At first, let me state the theorem for the quasi-polynomial-like functions. So we have the following characterization. If f is of the following form, then it turns out that this function is asymptotically R log concave if and only if all of its coefficient AL up to AL minus 2R are independent of the residue class of n modulo m. Now we can reformulate this theorem, to the A partition function in a bit more intriguing way. So we can state this theorem for the A partition function in the following way. We have that if A is a finite multiset and R is fixed positive integer, K is at least 2R plus 1, then the A partition function is R log concave if and only if every K minus 2R multisubset of A is coprime. And well, this characterization follows from other properties of the A partition function. Unfortunately, I don't have enough time to talk all about them. However, let us take at least a look on an example. For instance, if we assume that AK is given by the following equality, so it is a set which is actually a multiset which consists of the following elements, and let us assume that the cardinality of AK is just K. Then, in order to have to be certain that the corresponding AK partition function is 2 log concave, we need to know we need to have that K is at least 11. If we would like to consider 3 log concavity, then we need to require that K is at least 13, and so on and so forth. However, as I previously mentioned, 1 log concavity explicitly directly corresponds to the log concavity problem. And there are some more basic extension of the log concavity task. For instance, one can investigate the following problem. So instead of 1, we can take any positive integer m and ask about the following inequality. On the other hand, we can also assume that there is some parameter beta greater than 0 and ask how small beta can be in order to have that this inequality is valid for all sufficiently large values of n. On the other hand, one can also investigate the log concavity of the value of P of A of n over n to the power alpha for the fixed real number alpha greater than 0. And since all of these problems are very similar to each other, let me say a few words about the last of them, at least. So in that case, we have the following characterization. So this sequence is eventually log concave if and only if K is greater than alpha plus 1, and either K is 2 or 2 is between 2 and 3. In that case, we need to require that A1 equals A2 equals A3 equals 1, or K is at least 4. And in that case, it is enough to assume the assumption from the theorem from the previous slide for in the case of 1 log concavity problem. So that is this assumption that every K minus 2 multisubset of A is coprime. Great. However, there are some more intriguing problems, and And actually that are called the higher order Turing inequalities. We say that the sequence of real numbers C satisfies the second order Turing inequality if it fulfills the following inequality for all n greater or equal than 1. So it is just a weak version of the log concavity task. It fulfills the third order Turing inequality if the following identity holds for all positive integer n. And now instead of writing down all the inequalities directly related to the order d Turing inequality for each dB greater or equal than 4, let me state these problems equivalently. In order to do that, we can assign the Jensen polynomial of degree d and shift n, the sequence C, which is given by the following expression. And now it is known that the sequence C satisfies the order d Turing inequality at n if and only if this associated Jensen polynomial is hyperbolic, meaning that all of its roots are real numbers. And there is a very nice paper to Griffin, Ono, and Zakier, which delivers a very efficient tool to deal with the higher order Turing inequalities for various combinatorial sequences. And in fact, the authors proved that the partition function satisfies the order d Turing inequality for all sufficiently large values of n and every positive integer d. What about the quasi-polynomial-like function? Well, in that case, we need to require that this coefficient CL minus 1 and CL minus d need to be independent of the residue class of n modulo some positive integer m. And if that is the case, we have that the sequence satisfies the order j Turing inequality for all sufficiently large values of n and every j between 1 and d. I can reformulate it in the case of the A partition function and obtain that now we assume that every k minus d multi-subset of A is prime. And if that is the case, then we have the analogous result, the analogous statement, the analogous result for the A partition function. So it satisfies the order j Turing inequality for all but finite element values of n and j for all positive integer j between 1 and d. So let us take a look on an example from one of the previous slides. So if we set ak as before and consider the third order inequality, then we probably need to assume that k is at least 7. However, it doesn't follow from this theorem because we don't have that k that there is if and only if. So that's the problem with this characterization. I am still dealing with this task, but it's much more involved than the previous challenges. Great. So at the end, let me say a few words about the Basner-Ono inequality. And in 2016, Basner and Ono showed that the partition function fulfills the following inequality for all a and b greater than 2 and such that a plus b is greater than 9. And there are very similar results, very similar results for other variation of the partition function. However, we can also extend this theorem in a bit more different way. So let me recall that the generating function for the partition function is given by the following. And now let us take the right-hand side to the power x. Then we obtain on the left-hand side some family of polynomials. And it turns out that this family of polynomials also satisfies the Basner-Ono type inequality for all a and b which are given in this theorem. So we have some additional requirements on a and b and x. Thus, I have decided to investigate this issue for the A partition function, and I was able to obtain the following characterization. So if we have that the cardinality of A is at least 2 and the greatest common divisor of A is 1, then we obtain the Basner-Ono inequality for all A and B greater or equal than this very large number, which can be probably improved in a sense that it might be much more smaller. On the other hand, the most important thing here is that we cannot extend this theorem, meaning that the Boston-Ono inequality for the A partition function occurs if and only if these assumptions hold. And what about the polynomization? In that case, the generating function for the A partition function is given by the following quality. So once again, we obtain the some family of polynomials. And now I and Professor Bernhard Heim and Professor Markus Neuhauser were able to obtain the following characterization. So if A is such a multiset of positive integers that one occurs exactly once in A, and each number j may appear at most j times in A, then we have the following inequality for all x greater or equal than 5 and A and positive integer A and B, except the situation in which A equals B equals 1. In that case, we have some additional requirements. In fact, we have also obtained a bit better characterization in a situation in which A is a set, but I don't have a time to talk about it right now. So thank you very much for your attention. And at the end, let me just present some references of my talk.